So let's start with a quick recap of a couple of key things with probability. When we see something written like this with a capital P outside the bracket, that means the probability of the event inside the bracket's happening. So on a standard six-sided dice, the probability of rolling a 2, well, there's one way we can get a 2 out of 6 possible outcomes, the 6 possible numbers that could come up. So the probability is 1/6. We can write this also as a decimal or percentage. Generally, it's easier to stick to fractions. The probability of rolling a square number, well, on a dice we've got a 1, we've got a 4, so there's 2 possible ways to roll a square number, and it's good to simplify it if we can. Probability of rolling a prime number, we've got 2, 3 and 5 on a six-sided dice. Again, simplify it where we can. Now, mutually exclusive events cannot happen at the same time. And it's really important to make sense of this idea. So I've got some pairs of events here. We just need to think about which of them could happen at the same time, so they're not mutually exclusive, and which ones cannot happen at the same time, so they are mutually exclusive. So on a dice, rolling a 1 or a 2, that cannot happen at the same time, so they are mutually exclusive events. Rolling a 2 or an even number on a dice, well, 2 is an even number, so that can happen at the same time, so they're not mutually exclusive. Rolling a 1 or an even number, they're mutually exclusive because they cannot happen at the same time. Rolling a 4 or a number greater than 3, well, 4 is greater than 3, they can happen at the same time, so they are not mutually exclusive. Might be worth pausing the video and just having a quick think about these 5 pairs of events. Are they mutually exclusive or not? So the first one, 6 on a dice and tails on a coin, could happen at the same time, so they're not mutually exclusive. Hitting a bullseye and a triple 20 with one throw, impossible. They cannot happen at the same time, so they are mutually exclusive. Hitting a bullseye and scoring over 20 with one throw, well, bullseye's worth 50, so they can happen at the same time, they're not mutually exclusive. Pizza and pasta for lunch, you may not want to, but you could certainly have them at the same time, so they're not mutually exclusive. And winning a lottery prize and not winning a lottery prize, they cannot happen at the same time, so they are mutually exclusive. It may only be a small prize that you win, but you either win one or you don't win one. For mutually exclusive events, we can work out the probability with this formula. So the probability of event A or event B happening is equal to the probability of A plus the probability of B. So for example, if we think, right, we don't know what the probability of 1 or 2 is, but we could find it by probability of rolling a 1 is 1/6, probability of rolling a 2 is a 1/6. So probability of 1 or a 2 is 2/6. To work out the probability of rolling an even number, so that's the probability of rolling a 2 or a 4 or a 6, and that's 3/6. I know this is something we know without working it out step by step, but I'm just using it as an example to show you. So all mutually exclusive events add up to 1. So on a dice, all the mutually exclusive events are rolling one of the 6 possible numbers. So if we add those probabilities together, we'll get a 1. Remember, that means it's certain. It'll absolutely happen that it will be one of those numbers. Now, these are called exhaustive events, so all possible mutually exclusive events. And we use this idea to help us solve problems like this. So in a bag, we've got 3 types of counters, black, white, or red. So they're exhaustive events. It can only be one of those 3 outcomes from what we take from the bag. And we know they're going to add up to 1. So all we need to do to find out this missing probability here is work out what we get when we take away this and this from 1. So this is equal to 6/10. We've got 3/10 and 6/10. That leaves just 1/10, the probability of a counter being red that we take. Have a try with these two examples. So pause it, have a go, come back for the answers. So for the first one, we've got a spinner, it's biased, so it's not going to land on each colour an equal number of times, and it can land on red, blue, yellow or green. So they're exclusive events because it can't do 2 of them at the same time, and they're exhaustive. It's got to be one of the 4. So we can see here, we know the probability of it landing on red, we know the probability of it landing on yellow, and it says the probability of landing on blue is the same as the probability of landing on green. So if we add the probability of landing on red and yellow, the probability of it landing either on blue or green, we find by taking this away from 1, and that's 0.56. So because it's equal probability for blue or green, we can just halve that, and that gives us 0.28 is the probability for either. In the next one, we're given it as a ratio. So there's only red, blue or white counters. So they're mutually exclusive events and they're exhaustive events. It can't be anything else. A counter's taken from the bag and we're asked for the probability of each colour. So starting with red, if we do this as a fraction, there are 5 out of a total of 12 counters. So that's our probability. For blue, it's 4 out of 12, and for white, it's 3 out of 12. And checking these, we can see that they do add up to equal 1. Taking this a bit of a step further, the start is very similar. So we've got a spinner, it's got 3 mutually exclusive exhaustive events, and we want to start off by finding out the probability of C, because we're going to need this to estimate the number of times the spinner will land on C out of 150 spins. So as before, add up the probabilities we've got. We take that away from 1, and that gives us the probability of the event here. Now the extra step we've got, if we spin it 150 times, to estimate the number of times that will land on C, we do 150 times the probability for C, and that comes out to 81 times. Have a try on these two, really similar again. So first off, we need to complete the table here. If we add up the probability of red and blue and yellow, that comes to 0.7. So taking that away from 1, the probability of spinning a green will be 0.3. Spinner spun 60 times, we need to do it's for red, yeah, so 0.3 times 60, which will give us 18 times it will land on red. Remember, this is an estimate, it's probability. It's unlikely to follow that exactly, but it should be somewhere around that. The more spins we do, remember, the more the experimental probability, the experimental result will be in line with this theoretical probability. In the second question, we've got red, blue and white counters. So they're mutually exclusive events and they're exhaustive. It can't be anything else. So the probability of getting a blue counter is the same as that for getting a white. So for red, it's 0.2. That leaves us 0.8 split between blue and white. So 0.4 for each. The second part of this question is a little bit tricky. So there's 18 red counters in the bag, and we want to know the total number of counters. Now, the number of red counters is equal to the probability of getting red multiplied by the total number of counters. Now, we know there's 18 red counters. We know the probability of red is 0.2. And rearranging this, if we divide both sides by 0.2, we get 18 divided by 0.2. That will give us the total number of counters, and that's equal to 90. We can just check that. 90 times 0.2, yep, that does give us 18. Pause the video here, have a go at task 1. Now, if you want more straightforward practice, start at the beginning of the task, which begins on question 17, work through those. If you want a bit more of a challenge, go for question 22 onwards. They're a bit tricky, apart from one of them you'll see is nice and straightforward. Make sure you do, I'd say, at least 4 of these questions just for really good practice. Check your answers, they're attached as well. Now, this example takes it on a little bit. So we've got to buy a spinner. It's not going to land on the different colours the same number of times. And we've got the probabilities in our table here of landing on each colour: 0.08, 0.28, 3x and x. And that's just a way of showing what it says in this next sentence. The probability it will land on green is 3 times the probability it will land on yellow. So the probability of landing on yellow we've called x. 3 times that gives us 3x for green. Now the spin is going to be spun a number of times, and Darla estimates it will land on green 72 times. Final bit we need to work out is going to be how many times she's planning to spin it. But let's start off by working out the probability of rolling a green. So the probability of rolling red or blue is 0.36. If we take that away from 1, that gives us the probability it will land on green or yellow. So that's equal to the probability it will land on green plus the probability it will land on yellow. We've formed an equation which we can now go on to solve. So 0.64 is equal to 4x, and we just need to divide both sides by 4 to find out what x is equal to. So the probability it will land on yellow would be 0.16, and the probability it will land on green is 3 times this, is 0.48. Now, so we've seen she estimates it's going to land on green 72 times. So we know the number of green times is equal to the probability of green multiplied by the total number of ends. Here it's the total number of spins. So 72 is equal to 0.48 times the total spins, dividing both sides by 0.48. That gives us 150 spins. And just check with these, if you get a decimal answer, just check if that makes sense in the context of the question. And we can just double check this. We do 150 times 0.48, the probability for green, that does come out at 72. That answer does make sense. Have a go with this one. So 4 possible consequences: chocolate 0.14, a disappointing look 0.18, and we're told that the probability of nothing happening is 33 times more likely than detention. So if we call the probability of detention to x, probability of nothing happening will be 33x. Now we can follow similar steps to before. If we do the probability of chocolate and the probability of a disappointing look, that gives us 0.32. Take that away from 1 to find the probability of nothing happening or detention. So this is where we set up the equation. 0.68 is equal to 33x plus x. Collecting like terms there. And we can see that this is going to work out nicely. Divide both sides by 34. And that gives us 0.02 is equal to x. So probability of detention is 0.02. Probability of nothing happening is 0.66. Then we've got 9 detention slips in the box. So in a really similar way to last time, we know that the number of detention slips is equal to the probability of detention times the total number of slips. So if we do 9 divided by 0.02, that gives us the total. A nice straightforward way to do this without a calculator, if we multiply top and base by 100, we can see we've got a really nice straightforward calculation. There should be 450 slips in the box. And we can check that. 450 times 0.02 does give us 9. This next set of questions uses algebra in different ways, some of them similar to the last one, but there's a bit of variation in there as well. Have a go with these 4 questions. This is quite a challenging question. Might be worth taking time to pause the video and just having a read through it. So we're told we've got green and yellow counters, so mutually exclusive, exhaustive events. One's taken at random and replaced back in the bag, and the probability it's green is 1/3. So here at the beginning we could have maybe one counter is green out of a total of 3, or it could be that 2 counters are green out of a total of 6, so 4 would be yellow, or it could be that we've got 3 greens and 9 in total. We don't know at the moment, but we can write this as x over 3x. Now, 1 green counter is removed and 6 more yellows are added. So at the start we had x over 3x. Now x represented the number of green counters. We've taken one of those away, so we've now got x take away 1 for our numerator. We had 3x in total. Now, a total number, we've taken away 1 green, but we've added 6 more yellows, so we can tidy this up to get this equation for the counters now. And we're told that the probability of now taking a green counter is 1/4. So this is equal to 1/4, and we need to solve this to find x to then be able to fully answer the question. So if we multiply both sides by 3x minus 5, sorry, 3x plus 5, and if we multiply both sides by 4, we get this equation here. So then it's a case of just going through the steps to solve it. And we get x is equal to 9. So making sense of this, we want to work out how many of each colour are now in the bag. So here we had x minus 1 for the greens at the end. And the total number we had was 3x plus 5. So that's 32 in total, but to work out the number of yellow, we need to take away 8 from that to give us 24. And we can just check that it does work. So at the start, we're thinking that we had, if x is 9, we had 9 green, we had 27 in total, so that meant we had 18 yellow. So that's 1/3 of them were green. We then removed one green, so that left us 8. We added 6 more yellow, so that gave us 24. So in total we had 32 counters, and we can see that this 8 out of 32 is equivalent to a quarter. So we can double check that our answer makes sense once we've got the numbers there. So if you're after a bit more challenge, have a try with these questions. Make sure you check the answers as always.